Okay. Which screen do you see now?
We see a screen which is combined your presentation with also your background information. So that's probably not the appropriate screen.
Okay.
Not yet.
And I'll move this out of the way. Okay, so today, as already Leo mentioned, that the talk is focusing on microstructure, and
Elena,
I will be
just a moment. We do not have your presentation screen. We have your the screen that is
it's so, but why it said it post?
Do the swap.
Yes, already.
I don't think you pressed it. Maybe it's still active.
We still can see your preview of the next slide.
Yeah.
Interesting, because I swapped the screen.
Okay, then it's frozen.
Perhaps you can go out and stop sharing and restart sharing again.
Sorry.
It's all right. It's probably not in the presentation mode.
No, it's in presentation mode. The question
is it? Okay.
Why it's not? The second I'll get from presentation mode. We tried and it was shared. Okay. Okay, I'll do this share one. And okay.
Yeah.
Is it okay now?
Now
yes.
It's okay. Yes.
Okay. Sorry about this technical problem. So my talk will be focused on the two materials, steels and titanium, with the main focus on transformation-induced plasticity and twinning-induced plasticity effects. So I do conduct a very brief introduction to plastic deformation accommodation mechanism, and then move to talk a bit about high manganese steels, but the majority of my content is on titanium alloys and different factors and types of deformation accommodation mechanism and complex microstructures that developed in these alloys will be discussed. So why trip and twip steels? Because the standard steels that are usually strengthened by dislocation, movement, by precipitation strengthening, solid solution strengthening, have pretty small work hardening rate, and usually with increase in strength, we have a reduction in ductility. So typical stress strain curve is shown on this graph. And in the steels that we have, for example, a twinning operation or phase transformation, we have increase in both in strength and ductility. For example, twip steels could have strength exceeding 1 gigapascal with different elongations. Values could be up to 60%. And this type of steels that have twinning or trip-induced plasticity have very good formability, as we could see from the comparison on these two slides, where we have the standard IF steel and compare the depth of the cup and absence of defects for the twip steel. This is because of this combination of useful properties, including in energy absorption, trip and twip materials could be or find already or will be a suitable candidates for a lot of applications in different types of industries, which for steels, they are usually automotive industry and also structural materials, transportation, while for titanium alloys, about which I'll be talking also, it could be biomedical applications too, and aerospace industry. So trip and twip effect in steels were studied much earlier than in titanium alloys. And in steels, we have usually dependence on stack and fold energy, or which mechanism will be really operational. So with high stack and fold energy in austenite, and I'm only talking today about high manganese steels, which have austenite as a main phase at high temperature, and maintain mostly to the room temperature. So we have dislocation glide, and with decrease in stack and fold energy from 30-40 millijoule per square meter, we have initiation of first twinning in addition to dislocation glide. Then we have also twinning and partial Shockley dislocations glide. And finally, we have around 15 to 20 millijoule per square meter range where Martensite transformation started to be operational together with twinning. And Martensite, here I'll be talking about two types of Martensite, epsilon and alpha prime, that forming. And finally, at very low stack and fold energies, we have only Martensite transformation, and in addition to glide, and no more twinning takes place. For sure, it's not immediately when twinning or phase transformation will occur in the materials. We need to reach a certain state, and we call it, in a lot of cases, it was introduced as triggering stress, at which we have initiation of twinning or Martensite transformation. And usually it's an elastoplastic transition zone, and then it could be followed by the plateau or slow rising stress region. And in these regions, this is where usually the majority of events taking place. Triggering stress is an important parameter also, and sometimes in alloys on stress strain curves, we also observed so-called double yielding phenomena when we have second yield point later on. Triggering stress usually is a function of material composition and also conditions under which the test was performed. Because if you will be conducting tests, for example, in tension or compression, we will have different triggering stresses. For example, for titanium alloys, it was clearly shown that Martensite formation will be at lower triggering stress in compression than in tension. And if we have increase, for example, in beta phase stability in titanium alloys, triggering stress will be increasing. And for example, it could change from 180 megapascals to above 300 megapascals. So here's an example of formation just twins in 24 manganese steel. And we could see that as soon as we are reaching elastoplastic region, we have formation of the twins, and number and density of the twins clearly increasing. And due to these twins providing barriers to movement of dislocations, we have a dynamic hole patch effect, which is responsible in this case for significant strain hardening occurred. If we have lower manganese steels, such as 17%, in this range, it has stack and fold energy that is much lower, and we have only formation of Martensites happening during phase transformation, no twinning. So here we have a EBSD sequence of images at different plane strain compression values. Initial microstructure was consisting of hot rolled material. So red is austenite, FCC phase, green is epsilon, which is hexagonal, and blue is alpha prime, which is BCC Martensite. We have also yellow lines here, which is annealing twins, and also a bit of grayish like increased in here in set lines, non-index like stacking faults present in austenite. With deformation, we have increase in the formation of epsilon martensite on these stacking faults, and at higher strain, you could see that on annealing twins also will be preferential nucleation sites for formation of epsilon martensite. With further deformation, we have more complex network forming of epsilon martensite, and two competing events take place. We have increase in transformation, but both epsilon martensite and alpha prime martensite. But alpha prime martensite forming at within the epsilon martensite or in intersections of epsilon martensite, and gradually epsilon martensite fraction will be reduced and consumed by growing alpha prime martensite. Even epsilon martensite, in a lot of cases, preferential nucleation sites for alpha prime. Also, we could observe, as in this inset, formation of alpha prime martensite directly in austenite. At higher strains, we have majority now of alpha martensite formed with small remnants of retained austenite and epsilon martensite. And finally, we have a really very small amount of epsilon martensite, elongated grains even of alpha prime, which also undergone deformation and shear bending. If we look in TM, we will see that we have a bit of epsilon present in austenite here in initial state, but its number of packs of epsilon martensite increases with increase of strain. Further, the number increasing, they're thickening, and also we have a lot of stacking faults forming in austenite, which all assist formation of epsilon martensite and alpha martensite developing. And later on, we have a lot of now alpha martensite with epsilon martensite. What's interesting to look is on the substructure. I'm giving you just a bit of tease what we could do with high resolution TM as example that we could uncover in more details what's going on in epsilon martensite during deformation. For example, in a squench condition, we have austenite and intrinsic stacking faults present only in austenite. Epsilon martensite that present on quenching is free of any stacking fault or internal defects. Then when we have 5% strain, we have very tiny, very thin plates of epsilon martensite forming. And again, as you could see here, there is no stacking faults in epsilon martensite that just formed at 5% strain. However, with increase of strain just to 10%, we could see appearance of intrinsic stacking fault of I2 type. And this is typically we observed when thickness of epsilon martensite is below 20 nanometers approximately is the boundary. But at highest, or when it's thickened, and for example, 64 nanometer, here's example of thickness, we have change from intrinsic stacking fault I2 type to intrinsic stacking fault I1. So why this is happening? So we believe that when we're starting from ABC stacking of austenite, and when our dislocation partial moving on the each second layer, we have transition to epsilon martensite with the stacking AC and CAC, and then this deformation will continue and glide on the A layer will change and form it to B layer, and we will have AC, B, AC. So here we could see that AC2 we have AB stacking, change to AB, we have stacking fault C, again stacking fault AC. So it's pretty high energy configuration. Then when deformation continue and next dislocation could glide, we could change again of the stacking to AC, B, C, and this is ACF1, where we removed extra stacking plane, so the free energy is reduced, or stacking fault energy is reduced, and this is why we're observing change from one type of intrinsic stacking fault to another. And at high loads, we also observing a combination of basal and pyramidal slip in epsilon Martensite, which provides basis for the formation of extension twins 1 bar 2 and 1 bar 011 in this material. So this very short investigation provides us with some insight into the formation in the sequence of epsilon Martensite and alpha prime Martensite formation in this material, and also in deformation behavior of epsilon Martensite. So this is probably all that I want to share with you about steels. And to summarize, we know that depending on stacking fault energy of austenite in austenitic high manganese steels, we have different deformation accommodation mechanism operating that could combine either one of them in addition to slip or combination of phase transformations, which could be either, for example, alpha prime Martensite could form directly from austenite or via epsilon Martensite formation. And also we have twinning could take place if we have higher stacking fault energy than in situation when only Martensite transformation could occur. What also I would like to point out that despite these materials having very attractive strength and ductility properties, yield strength remains pretty low. So for a lot of applications, its demand will be to increase yield strength, but maintain the good ductility and formability in these materials. So now I will be moving to titanium alloys. So this is a diagram that's showing classification of titanium alloys based on phases. And as you could see, with increase of beta stabilizing elements, phase composition changed from alpha to alpha beta to beta. The topic of today's presentation are only metastable beta titanium alloys, which could maintain beta phase to room temperature, but transform under applied deformation. So what mechanism could operate during deformation in these materials? The first I will talk about is formation of alpha double prime Martensite with orthorhombic lattice. In some titanium alloys, we could have also alpha prime Martensite forming, but usually it's in the materials with lower alloying or less amount of beta stabilizing elements. So this is why I will be focusing only on alpha double prime Martensite, and orientation relationship between parent beta and Martensite are presented here. The next is again twinning, and in reality, what we learned a lot on steels was driving force to study more what's going on in beta titanium alloys. For sure, there is a difference that in trip and twip steel we're mostly dealing with FCC as a parent phase, while here we're dealing with BCC parent phase. And if in steels we have only one type of twins commonly forming, here we have two systems, 332-113 or 112-111 that could form. And also In steels, we have epsilon martensite, additional phase transformation forming. In titanium alloys, we have deformation-induced omega phase that could form. So beta phase stability is a main parameter that dictate which of the deformation mechanism will operate. And beta phase stability will depend on several factors, including composition of the material, also grain or beta domain size. What is the difference between grain and beta domain size? So the main difference is that in some metastable beta titanium alloys, sometimes it's called near alpha alloys, we could have some alpha phase formed. So the region in such alloys or volume that doesn't contain any alpha phase, we call it beta domain size. And also presence of a thermal omega. A thermal omega could be formed on cooling, accelerated cooling or quenching from higher temperatures, and typically in the range between 500 and 200 degrees C. Or it could be formed on heating or on as a thermal holding. Presence of a thermal omega may have effect on martensite and twinning. Also, grain size, grain orientation or texture of beta grains will play a role, and deformation conditions, which not limited to, but could be strain rate, and also whether it's load in tension, compression, torsion, and so on, bending, so, and temperature also. For sure, there are so many conditions and factors that I will not be able to cover everything in this short lecture, but no, reasonably short lecture, but I will try to address the most important parameters that I think of interest. So beta phase stability is typically could be predicted using so-called MD-BO approach. So metal d orbital and energy level, and bond order, which is strength of the covalent bonding between titanium and other atoms present in the material. So this is one approach for design such materials and predict their mechanical behavior. And another materials that some using are molybdenum equivalent calculations, in which contribution to the stability comes from all beta stabilizing elements, and subtraction from the alpha stabilizing elements, for which aluminum is the main one. It's a common to call it Morinaga phase stability diagram. This is extended one. Originally was a bit smaller one, and now it's extended was to 2.96 BO. And here we could see a relationship of fields in which we have operation just of the slip on the here in beta phase. Then we have the region of twinning taking place. Also here was added to this diagram a region where we could have deformation-induced omega operation. And here we have martensite formation. And for example, here we have alpha phase, but we are dealing, as I said, only with beta phase transformation in these alloys. This is just a summary that was done in review by Coley, which shows us which mechanisms were experimentally detected in variety of alloys as a function of molybdenum equivalent. So as we could see at very low levels of molybdenum equivalent, we have only martensite transformation happening here. Then we have a range of intermediate values where we have martensite, twinning, and slip. And at very high levels in very stable beta phase, only slip operates. So I will start first talking about martensite formation, and then we'll move to omega and twinning and their combinations. So typically, according to orientation relationships, For a random situation, we could have up to 6 variants formed in one grain of beta phase. However, when we have application of load, the variants are not formed randomly, but we have so-called variant selection. And standard approach to predict which variants will be forming are usually as the one that produce the maximum transformation strain. Also, self-accommodation of by alpha double prime variants of strain accumulated in beta matrix as a result of formation of the first variant leads to the special configuration or arrangement of the next forming alpha variants. And they could be mostly to achieve the best accommodation of strain. It will be either type 1 twinning, where they have the common 111 alpha double prime plane, or type 2 twinning, where they have common 211 alpha double prime direction. Also, formation of fine 111 twins observed within any alpha double prime variant. And because it's continuous process during deformation, we have formation of alpha double prime, but earlier formed plates of martensite start to deform. We could also observe twinning within this originally formed alpha double prime martensite plates, and deformation twinning also could be of two types, 130-310 and 110-110 type, but in majority cases also not always, but at the beginning of deformation, the operation of which system exactly operates will be depend on the Schmidt law or orientation of the grain, which is related to orientation of the grain. Also, we could produce special inverse pole figures that will show us which orientation will be the most favorable for formation of variants with maximum transformation strain. This work was done by Kim and Gao, for example, and we could see that here we could produce these maps for any direction in the material crystal, in the polycrystalline material, but independent on the composition, because you could see that it's titanium 10 niobium, titanium niobium zirconium, or titanium niobium tantalum. The maximum transformation strain will be for orientations will be near 0.11 beta. However, in titanium niobium alloy, the values will be here. You could see 8, and here is with the tantalum addition is 2.4 only. If we're moving towards 0.01 and 1.11 poles, we could see that we have a reduction in these values for all of the materials. So this, we could use data from synchrotron, XRD, or neutron diffraction to insert in this calculations to form, to plot this particular diagrams. Also, not only the composition, but the mode of deformation will affect which variants will be forming. Here is the work that done mostly by Frank Nissen when he was also in Wollongong with us. And we could see here that 3 different composition or alloys compared, and common, only here I'm just showing only 4 common modes of deformation, like uniaxial tension, compression, balanced biaxial tension, and pure shear. And you could see that predicted available work for different stress states is really different. So it's similar for the alloy for different compositions. we have slight difference in intensity, and we could see that Martensite transformation will be here for titanium, vanadium, iron, aluminium, probably will be the highest available work values. You could see intensity colors is much higher here. While for titanium, molybdenum, it's even will be less than for titanium, 16 niobium, 3 aluminium. But as soon as you change type of loading, you could see that distributions are changing. And because we have different areas in which we have different available work, we will have different potency of the which variants will be forming. And here, as you could see, for again, composition has pretty small effect, slight change in the fields, but very, very minimal. But when we're moving from one type like tension to compression, we could see that we have changed from variance numbers 5, 6, and 1 to variance 3, 4, and a bit of 5 still. But anyway, from 3 variants to 4 variants. And here we have only 2 variants will be selected, predominant. Okay, so important to understand how not only the composition of material, but also how the stress state affects the development of microstructure, and in this case, Martensite Variant Selection. And if we do neutron diffraction, for example, studies, we're getting bulk information. And this is, we have pure beta initial microstructure and alpha double prime forming. Here you see alpha double prime forming after reaching the triggering stress required for its formation. And if we have material with higher stability of beta phase, because if we have a bit of alpha phase formed, and it means that beta stabilizing elements diffusing back to the remaining beta phase and increasing its stability. So we could see that triggering stress also increased for this material when it has more alpha phase than compared to 100% of beta phase. And if we look in 2 directions from axial and radial directions on our patterns, we could see that there is a difference in intensity in alpha double prime and peaks, and which also indicates some variant selection. And here we did further analysis, and as you could see, green line is a change in the volume fraction of alpha double prime. And you could see that it started to appear in elastic plastic region. And the majority of phase transformation from 0 to 70% take place in the slow rising stress region, which corresponds also to significant increase in work hardening rate to the peak. And then we have only small increase in volume fraction of alpha double prime from 70 to 80%. And here we have already decrease in the rate of work hardening. What's also interesting, if we look at IPF for this material, this is corresponding to pretty low strain 0.038. And we started with very weak random texture in beta phase. And here we have development of 210 component. And this is usually associated with some twinning effect taking place, possibly taking place in the material. And then Martensite forming. And we could see that from this pole or texture fiber, we have formation approximately around 0 to 1 alpha double prime fiber. And this fiber is only 5% deviation from 031. And why 031 of interest? Because this particular variant, when we have 012 transforming to 031 according to the standard orientation relationship, but it has the largest transformation strain, and it enables the most efficient accommodation of the deformation. If we now look at the microstructure, we're starting from fully beta microstructure, and here we have formation not in all, but in selected grains of some deformation products, but some grains are still remained undeformed. Then we have, by the end of the slow rising region, we have nearly all grains having deformation products, and density and fraction of deformation products continue to increase later on, but less fast, let's say. So now if we look in TM, we could see that initially we have single variant of Martensite plates forming in one grain. And within these Martensite grains, we have striations like columnar ones. Typically, it's considered to be remnants of or evidence of the passing of dislocations during the shear mechanism of the formation of Martensite. So this is a sticker plate that we could see it. This is small plates of Martensite just forming, and this is nice tip is propagating in beta matrix. And also here we see a lot of small dots in the matrix. This is the beta matrix, and this is where a thermal omega phase is present, and no thermal omega phase in the Martensite due to shear mechanism of its formation. At increase of load to 2.6%, we have much more extended phase transformation of Martensite. Now we have multiple variants forming, and they are accommodating, self-accommodating the strain as expected. You could see that they have one type twinning formed, so shared 1-1-1 plane, as we could see clear here. And if we look here, we also could see that each variant, we have like variant A Martensite, then variant B, variant C forming. They're all in the same orientation relationship and sharing 1-1-1 twin plane, and secondary 1-1-1 twins forming within each one of the primary planes. Finally, at fracture, what we have seeing not only what is similar to previous arrangement, but just very small amount of beta phase left. And what's interesting also that inside the plates, we now have not only inclined 1-1-1 twins formation, but sort of mid-rib alpha double prime twin, but this twin is still having the same 1-1-1 type twin. Also, if we continue to look at some regions where you have intersections of the different variants of Martensite. So here is dark field image, and one variant is light up, and the second variant is a dark one. So I just would like to draw attention to this intersection, where with the second variant is coming, the ones that are forming grid, and it's crossing one of the plates, but it's stopped and a bit of bulging here, and it's not really propagating through. It's due to the strain here within this plate. The next plate is really nucleated at other side of this Martensite plate and start growing. This is experiment of the bending that was carried. Oh, sorry, went This is the same 10 vanadium to iron 3 aluminium alloy. And here we're looking into the bending test. And we will see now, we see that we have formation of products, grid, and then in these grains it started later, and also more variants forming near the grain boundaries. So analysis of variance formation was done here by Frank, and this is, if we overlapping, this was first variant, second, variant 4, and variant 6. And what's interesting, if to do analysis of available work done for, again, for variant selection, here is 4 grains. So grain B4, B7, B5, and B6. So for grain B4, we could see that we have variant 3 and variant 4 favored. And this was predicted to start with by the calculations. In B7, in this one, again, variant 1 and variant 2, and they are 1-1-1 compounds twins, but they were formed at higher levels, strains than the first ones. And what's also happening that in B5 and B6 grains, the formation of variants started later, as you saw on the video. Hopefully it's rotated, but this is what we observed. And it's typically, it was no favored variant, and Martensite formation started at much higher loads. And we think that these grains were less favorably oriented to the deformation. And this is why the accommodation of deformation was started at higher levels and shared by the several, again, 1-1-1-1 type 1 and 2-1-1 type 2 twin relationships. However, the available work analysis also was not accounted for variants forming in the vicinity of the grain boundaries. And careful look at these areas showed that this also accommodation of strain out of plane deformation, which is also not predicted by the modeling. And also when initially some variants formed, the surrounding matrix changed the stress state. And again, this is not accounted in the prediction because we are considering initial state of beta matrix without already taking place phase transformation. So we could say that we could use approach of available work or formation of variants with the maximum transformation strain only for initial stages at lower loads, and this approach will not be applicable at later stages of the deformation. Also, if we look at interaction between different variants of Martensite, so we could see from just snapshots of sequence of events taken in this area, from single plate to several plates in the same direction, then perpendicular grids, and then variants under the angle forming. And then if we do EBSD analysis, what was shown that at intersection or at impingement areas, we could see formation of deformation twins, which is 310-130 type. The question is interesting, whether we have reversion of Martensite when we released the load. Why this question is of interest? Because in some materials, we're looking only ex-situ, and we may not know whether we're looking at real situation, what material had during applied load, or that some changes took place. Furthermore, it was suggested by Castani and others that if we have already Martensite formation in titanium niobium alloy, and it has much more significant number of 130, 310 twins forming, then these twins on release of stress could be reverted to 332-113 twins in beta phase. And typically we see a lot of 332-113 twins in beta matrix. So this is one of the possibilities, and really, yes, reversion of Martensite in titanium niobium alloys was observed because these are superelastic alloys, and it looks like its reversion takes place easier than in other alloys. Also, please note that it was loaded only up to 5%. Here's another work on 10-3 alloy by Dannard, published pretty recently. And here we could see again 5% tensile loading, and yellow here is alpha double prime around alpha particles, and in the here you could see. And when load and also twins are present independently under load, here 332 twins, as you could see. But when load was removed, there is a partial reversion. As you could see, only a small amount of Martensite remaining in comparison with loaded condition. In the case of our study on the similar alloy 10-3, we have load to 1450 newtons, which exceeds 5% tensile loading. And on unloading, we didn't observe really any visible changes between loaded and unloaded condition for Martensite. So I think it's not only the type of alloy in which Martensite is forming, but also how far you loaded your Martensite, whether any other maybe changes in Martensite structure took place that prevents easy reversion of the Martensite. But I think this is an interesting topic that requires further studies in situ. Okay, in addition of Martensite formation, we have also deformation-induced omega formation. What is the difference between athermal omega and deformation-induced omega? So here in dark field, we could see small bright spots, which are really very tiny nanoscale athermal omega present in beta matrix. Contrary, we have seen this line, they're pretty thin, but they're really plate-like or less like structure and significantly elongated in direction. Typically, we could see two variants of athermal omega formed in grain, while we have only one variant of deformation-induced omega present. And in both cases, the same mechanism of the formation of omega probably exists, which is involve atomic shuffle in one bar 1 beta on direction to bar 1 bar, and also depends on the transition state. We could have partial collapsed or full collapsed, so-called, in the structure, So B prime here, as you could see, these two atoms is partial collapse, and here we have full collapsed. So this is fully developed structure of unit cell for omega phase. So here we could clearly see at also what's interesting, that without load we have usually two variants of omega phase, and if we have operation of the slip taking place in beta matrix, we have channels of omega free regions as pointed here by the arrows, and this is because specifically oriented variants of omega could revert back to beta phase on applied load, and this is why these areas are clear from when dislocations moving, clear of a thermal omega phase. So here we could see clearly this is thin layer of omega phase forming deformation induced, this one, and at high strain the thickness of deformation omega could be slightly larger, but not by much. So we don't see very large abundance of deformation-induced omega forming in directly in beta microstructure, as you could saw on the previous slide. It's in some areas only we could find such packets, but it's usually not the dominant deformation product that we observe in the microstructure. But also omega could be forming not only directly in the beta phase or to be fully surrounded by beta phase, but in the cases when already we have formation of alpha double prime, like shown here, this is alpha double prime, as you could see from the diffraction pattern from this area, and then we zoom in into this area. So this is pretty small alpha double prime plate forming. This one, it's a bit expanded, and now we will have high resolution image of the interface, and we're clearly seeing that we have formation of layer of omega phase between alpha double prime and beta. And this was earlier reported in Raber's group, that such observations were for a thermal martensite formation, but here we see it during deformation also taking place. And it was also suggested earlier that for both the case of alpha double prime formation or twinning that taking place in beta phase, usually there is a strain field or stress field around the formed alpha double prime plate or twin plate, and typically we have the shears that will be forming in these areas at interface between martensite and beta phase, and it will be, in this case, existence of this shear will help in overcoming the energy barrier for the formation of omega directly from the beta phase. This is why it will be preferential place for omega phase formation, and also I think it's relaxing really the accumulated stresses in this area. Okay, let's talk about twinning. And we could see here an example of formation of 33211 twins in titanium 15 moly alloy. So this is a pretty stable beta phase condition, and mostly it was reported only twinning in this material, as it was done by Min and others. So just we could see clearly similar that you saw in TWIP steel, high manganese steel, with increase in strain amount of the twins start to form first in preferentially oriented grains, then it's in all grains, and number density and complexity of twin arrangements increases from parallel ones to complex grid arrangements. So this was formation of 332-113 twins, but in titanium niobium alloys, different alloy composition, the dominant twin system will be 211-111 beta. And again here, what was shown that in addition to formation of these twins, the formation-induced omega interfacial layer is formed around. So again, this is the same work by from Rabe's group, and so we have joint formation of 111 twins with the formation-induced omega formation. And again, it's the same explanation was that stress is formed in the beta matrix resulting from this twins formation help to overcome the energy barrier for omega formation in beta phase. Let's go back to our studies on titanium, 10 vanadium, 3 iron, 3 aluminum alloy. And here we have a joint operation of several deformation mechanisms. So in addition to 332-113 twins, we have formation of also 112-111 and alpha double prime martensite. So it's probably the only point, or 2 points that I would like to make here. That first, kernel average misorientation clearly show that there are strains present around twins formed, and this is why, as in previous case, it was also implied, this is where could be omega phase forming in these areas. The other point that whether all twin systems that formed in one grain are formed according to the Schmidt law. So analysis of 4 twin systems formed in this one grain is given in this table. And we could see that 33-2-113 variant has extremely low stacking Schmidt factor. Typically, it should not have been operational because typically you need to have about 0.3 or more Schmidt factor for twin system to operate. However, the next one, this one, you see these thick parallel lines, they're thicker. They probably more form earlier, and they have higher Schmidt factor together with another one with systems that have high Schmidt factor, which is more preferential for its formation, and another one again have low Schmidt factor. So I think we would like to suggest the same explanation as for application of predictions for Martensite variant selection. The same is for prediction of the twinning systems operation, that the twins forming first would follow the Schmidt factor, and the twin systems with the higher Schmidt factor will be operational. However, in the remaining beta matrix, the stress state will be changed. And in these areas, and also in the areas of the grain boundaries, the conditions will be completely different from the initial conditions. And this is why, if according to initial calculations, the twinning system formation will be not favorable, it will become favorable at higher loads. Have a look in TM. We will see that we have formation of twins. It's highlighted here. These are 332-113 twins. And also we have more layers of products forming, because within these twins we have abundance of deformation-induced omega, and you could see that the number density is much higher for this omega phase compared to the omega phase formation that we saw formed directly in the beta phase, not within the 332-113 twins. And also it's oriented, perpendicular to the boundary of the interface between the beta matrix and the twin. This was explained by Furuhara a while ago, that also using Takimoto's suggestion that relaxations of atoms along 111 beta near interface of twin beta matrix, but within the twin area, may induce or be preferential nucleation and formation of deformation-induced omega. What else we could see, that in addition to deformation-induced omega formed, we have also formation of 112, 111 twins. As you could see, this goes like these ones across the 332, 113 twin, and also along the interface between 332 twin and beta matrix. So high resolution image taken from this interface. So this area is clearly showing us that this is 112 twin is lying at the interface. And also we observed formation of deformation-induced omega in two other locations associated with 332-113 twins. One is also at the interface, similar as in the previous case, we saw formation of the 112 twin. Here we have formation of deformation-induced omega at 332 twins beta matrix interface. And here's the same, another example. And also another example that we have deformation-induced omega going not along across the twin, but inside along the twin also, 332 twins. For all this mechanism of deformation-induced omega formation, still the same orientation relationship between either twin and deformation-induced omega, or between matrix beta and deformation-induced omega maintained. Also, if we have, typically we observed formation of 332 twins when we have relatively small amount of alpha phase formed in this material. It means that we have a bit less stable beta phase. And when we have higher beta phase stability with larger amount of alpha phase present, we will have formation of 112 twins directly inside the beta matrix. Also, at high strain rates, was interesting that formation of 332 twins was predominant, and at very low strain rates and in stable beta phase, we have dominance of 112 twins formation. There is a very interesting hierarchy of different products formed in these titanium alloys. This is not our work, but I just would like to give you two examples, one for titanium molybdenum alloy and one for titanium 10 vanadium 3 aluminum 2 aluminum 3 2 iron alloy. And so here in work by Mantri, they clearly also showed what we also think, that we have formation of primary 332 twins, then it could be secondary 332 type twins forming. Then there are tertiary 112 twins forming inside 332 twins. So as you could see here. And also, if to zoom in more into interfaces between and within these twins, you could see that within the primary 332 twin, they have such attached band. And in this band, it was remnants of Martensite visible and remnants of, and a bit of deformation-induced omega. So it was also idea was that possibly that it was fully martensitic band, but on load removal, it was transformed back partially to beta phase. But as you could see, we need really a lot of detailed in-situ experiment to fully elucidate the sequence of phase transformations taking place, which forming such complex microstructures. And this is in our 10-3 aluminum alloy. Again, here we have network of 332-113 twins. So this, they all here, and we could see increased magnification that showing clearly that it's 332-113 twins. And if we zoom in now within this primary products of 332 twins, like here, this one, we could see that within we have two variants of Martensite forming inside. Again, they have compound twin relationship. And if we zoom in into this area, we could see that again we have Martensite forming inside the 332 twins, and within this primary Martensite we have secondary Martensite forming. And in remaining in this area between twins, 332 twins, so it's remaining beta area. If we zoom in, we could see that this is our 332 twins with Martensite forming, but in remaining beta area, now we have formation of alpha double prime, which are small thin ones only, but directly from beta phase, not inside the twins. So as you could see, we have very, very complex sequence of events that taking place during deformation of titanium alloys, which depends on not only on the composition of the alloys, the stability of Martensite, and whether it's revert on unloading, on the stability of beta phase, on stress state that caused by different load conditions, strain rates, or change in the strain path. So this is a really fascinating area of research, and I believe that a lot of further research in this area that will combine in-situ characterization with modeling will give us a better understanding of operating mechanisms. So this is just acknowledgement of a lot of people that contributed to work that was part of these presentations. Both majority was at University of Wollongong, even visitors that were there, but also had collaborators in the Institute of Metal Physics, and also valid discussion with Professor Furuhara on this topic. And there is some support that we got financial from different grants. Thank you for your attention, and I'm open for the questions.
Thank you, Elena, for a very inspiring and detailed, indeed, microstructural lecture on the local deformation mechanisms involving phase transformation. I'm sure there are many interesting questions. So may I propose that people who would like to ask a question either raise their hands by clicking on the reactions button, or either type the question in the chat window.
Should I stop share, or because I will not see probably chat, or you will tell me about the question?
Yeah, I have the chat window open here. So also I will now finish the recording. Okay, so recording will stop now because the Q&A we will not record.